let us look at the store instruction. Actually, that might be a better thing to do first. Okay, let's look at store word. Right, so we are basically saying SW x1 x2 of minus 10. Okay, some immediate data basically. So SW x1 x2 IMM. Okay, so again, if you look at this, it's the PC that is sort of launching, right? So we are trying to store some register value into the memory. Okay, so therefore really what are we talking about? We are talking about the memory which has to be the capture flop here. Okay, so if you look at this guy, we are talking again of TPC QPC. Okay, then we are talking about fetching the instruction. Then there is a decode happening here. Okay, now what is going to happen? You have fetched x1 and x2. You are going to read these two data, right? So in some sense, what you are going to do is you are going to take the data of x2 and so what you are going to do here is you are going to read x2, okay, and then you have to add 1 to this, right? Right, and yeah, so let us look at this operation. So we are going to, get the value of x2 here, okay, which is going to appear at this point, right? So maybe I'll put this in magenta or something, x2, and this immediate data minus 10 is going to come as some 12-bit number that is going to sit here, this 31 to 7, right? And that was available at what point? Just TPCQ-PC plus TMEM. Just after that, that data is available, right? But it's going to take a T decoder time for you to decode and figure out, okay, who is this, what is the immediate source and how it should be interpreted, right? So therefore, you will have a T decode going through this guy, okay? So you will have a T extension, right? You're going to come through that, and then you're going to go through this, you're going to have a T decode plus T extension for data to be available at this point, right? So that minus 10 gets sign extended and then it is going to come here at this thing. So this will be some minus 10, okay, minus 10, and this ALU result has to be evaluated and it is going to go to the address, okay, it is going to go to the address. Then RD2 is my second source register, right? Second source register, which is basically going to come and is the register that is going to get written into the memory. So therefore, x1 data will appear here, okay, and you have x1 sitting here, and so remember RD2, the second register is got read out, but it is not getting used by the ALU. It is just being bypassed directly to the write data of the data memory, right? And then in the meanwhile, while the decoding was done, the write enable of the memory has gone high, right? So that it is all ready to be written. Remember, in order to write data, it's a sequential process into memory or register file. You have to enable, write enable, and then the clock has to assert. So the clock, when the clock goes high next time, data gets written into that particular location, right? So therefore, if you look at this, what you are going to do is, yes, there is now a TALU operation happening here. TALU is going, is going to evaluate this x2 minus, x2 minus 10, and then that's going to get treated as an address, and data is now ready. It has to just be ready there. Okay, there's nothing to do. It will get written in the next clock cycle. Okay, so therefore if you look at the TC min here that we are talking about, TC min for load, okay, sorry, store word, not store word, we are talking about again TPCQ of PC plus Tmem, right? Then we are talking about the T decode, because when you look at, again, when you look at this particular point, we are looking at the maximum time at which these signals will arrive. It is therefore going to be this T decode plus T extend plus T mux, basically that is going to, you know, take its time there, right? And there is another operand which is coming from here, right? So therefore it will be just max of T RF read, right, plus T decode, sorry, this is comma, not plus, T decode plus T ext plus T mux. Okay, so we are looking at this path here, which is T RF read, and we are looking at this particular path which is coming T decode later, and then you are going through this which is T extension, right? So this is T decode, right, and therefore, and then there is a T mux here, okay, and therefore source B will be ready only at T decode plus T extension plus T mux, and therefore you have to look at the maximum of T RF read and this, and that's when that data will be ready. Then the T ALU, okay, and at now there is no data that has to come back to the memory or anything like that, right? So we are just dealing with, so if you look at this, it is simply going to be the memory read is actually not happening, okay? It is just the setup time that is needed for you to set up the data before the clock edge, if you look at it, okay? So that setup, so I am going to call that plus some T mem setup, okay? So TPCQ, T mem, so let's look at this. We were talking here of T decode, right? But the key idea is that you do exactly a similar thing. You take read two registers out, you're going to compare it in the ALU, and then the 0 signal is going to get set, it goes back, right, as an input to the control unit, and then that is going to determine your PC source, okay, whether you are doing PC plus 4 or PC plus some immediate data effectively, right? So remember, now in the branch or equal alone, the ALU time is not the time that will get used, because to do that addition, right, it's only the ALU is only to use to compare the two registers. When you want to do branch on equal, you're trying to compare the two registers. On the other hand, in order to do PC plus immediate data, there is a separate adder that is sitting here, which is different from the ALU, and therefore that delay of the addition, right, will already happen, be ready and all that, but it will be determined effectively by the time it takes for the ALU to sort of execute, okay. So I leave that as an exercise to you. Now, amongst these, which one is going to be the slowest operation, right? So the key point to note here is that the load word instruction, right, load word, if you look at LW, right, x1 comma x2 minus 10, right, we are trying to evaluate x2 minus 10, give it to this thing, and then you are trying to read that data back from the memory. Okay, so therefore if you look at this critical path, right, ultimately the clock period, minimum clock period will be determined by this particular operation load word. Okay, so here again you will start off with T PCQ PC, then you go through one T mem. You are trying to read this, the instruction has come, right? Load word involves a destination register, so this guy will correspond to X1 register, right? And then you are going to say, okay, this guy will correspond to X2. This source B to the ALU has to be this minus 10. Okay, so minus 10 will appear here, and then so maybe I'll use a different color because timing is, yeah. So effectively this is going to be my X1, this is going to be my X2, this is minus 10, and then you are going to sign extend that, right? So anyway, so now you go through T decode, right? Then you go through T RF read, right? So then this has appeared again like the store word. This is going to take its T decode for it to appear, this IMM source, right? And after T decode it's going to take, so therefore this will be ready. Okay, if you look at this, it will be TIMM plus T decode. Okay, and then you're going to go through a T mux, then you go through a TALU. Why? Because you have read out the contents of X2, right? You have read out the contents of X2 on to source A here. Okay, the contents of X2 has come out here, right, of the register. The immediate data is here, which happens to be minus 10. You get the result after TALU, and then you do another killer operation, which is read data from this memory. Okay, you're going to read data from the data memory. So therefore now you will incur another delay after this address is all available, remember, right? So the address is going to take, you know, a TALU after it, the source operands to the ALU are ready, and this takes another TMEM, right? And then you take another TMUX, right? And then you come back, and this has to get written back into the destination register. So this is where the final operation is going to happen, right? So if I look at the delay associated with this load word instruction, and I look at the minimum clock period, right, TC min for load word type of instruction, right, then we basically have T PCQ PC, okay, plus T memory plus we are going to now look at the maximum arrival time, right? So we are going to look at max of T RF read, right, comma T decode plus T extension unit plus T mux, okay, plus a TALU, okay, plus TMEM plus TMUX plus TRF read. Okay, so when you compare the R type, the S type and the load word, store word, load word, R type, clearly the one that is going to dominate this whole delay process or the rate determining step as they call it is obviously the load word instruction, and therefore this is the slowest operation in the microprocessor, and if you can handle this operation, you can handle any other operation appropriately, right? So coming to a single cycle performance example, let's assume that a program spits out 100 billion instructions in the RISC V processor, right? The execution time to refresh your memory is number of instructions into cycles per instruction into the clock period. So in order to calculate the execution time, we first need to calculate the clock period, okay? So what is the TC min ultimately? It is basically the max of the clock period of all types of instructions that we discussed was the dominated by the load word, and therefore let's go ahead and calculate this. Basically we have, let me just put that expression here. You can see it on top. T PCQ PC, which is 40, right? Then we are talking about 200 instruction memory delay. Then we are talking about the max of RF read. So if you look at T decode, right, it is 25 plus T extension unit is essentially 35, that is 60, and T mux is how much? It comes out to be about 30, right? So we are talking of 90 picoseconds. On the other hand, the register file read is 100 picosecond in this example that we have considered. So therefore, it is the RF read that is going to dominate this process, and therefore I will just put 100 here plus the ALU delay, which is 120 picoseconds, plus the memory delay again, okay, which is essentially going to be memory delay is how much? Again 200 picoseconds plus the multiplexer delay, right, which is going to be let's see 30 picoseconds if I am not mistaken. Yes, 30 plus the register file setup, which is 60, right? So if I add all this, I will get 200 plus 200 plus 100, 500, then 60 and 40, another 100, 600, right, 600 plus 120 plus 30. So we are talking of 750 picoseconds, right? The clock period therefore for this RISC V implementation is 750 picoseconds. The number of instructions is 1 billion, right, or 100 billion instructions, I'm sorry, 100 billion instructions in the example that we have considered. Yes, so it is 100 into 10 power 9, right? So the cycles per instruction, because it's a single cycle implementation, is just 1, therefore number of clock cycles is just 100 billion into 750 picoseconds, into is just 100 billion clock cycles, right? And therefore execution time, program execution time is just number of clock cycles 10 power 9 into the clock period, which is 750 picoseconds, and pico is 10 power minus 12 seconds, right? So therefore you have 75 seconds, that is the program execution time for this 100 billion instruction program.